Welcome to Math 31. This is a lesson on the quotient rule. So given a function y is equal to f over g, now I didn't note this one already, and I will. G cannot equal 0. F over g prime would be equal to f prime g minus f g prime over g squared. So it's got kind of a more complicated form than does the product rule. Now the other notation for this, or one other notation, is Leibniz notation. So if you were to take the derivative of a function u over v, it would be equal to the derivative of the u function, let's say with respect to x, multiplied by v, untouched, minus the u function multiplied by the derivative of v with respect to x, all divided by v squared. Now, unlike the product rule where you're adding them together, so it doesn't matter what order you differentiate the individual functions, here it does matter. It's got to be du multiplied by v subtract u multiplied by dv. Now, the way that I like to do this one is similar to what I did with the product rule. Given y is equal to uv, y prime is equal to u prime v minus u v prime all over v squared. So that's a compact way. When you're solving it yourself, I recommend using that. Now you may want to transfer back to Leibniz notation at the end, although it's not critical that you do so. I typically will. But when I'm working through a problem, I like to keep it in this clean, simple form. Now, you've actually got a series of questions on your notes, 5 of them, then the proof, and I'm going to go ahead to the proof first to dispel any lingering doubts about whether this is actually correct or not. So I will go ahead to that, and then I'm going to go back. So the proof of the quotient rule starts with being given a function f of x is equal to p of x over q of x. Now this proof is not as complicated as is the product rule. Now, given this, if we were to multiply both sides by q at x, we would get this statement: f at x times q at x is equal to p at x. And now, I'm going to differentiate both sides. So that would mean, using the product rule, which we have already, and it has been established that it's correct, that would be equal to f prime at x times q at x plus f at x multiplied by q prime at x. And then that's equal to p prime at x. Now, I'm going to isolate f prime at x because that's what we ultimately want. Right there. Because we are trying to find the derivative of f at x. So f prime at x, if we do all the manipulation on it, would be equal to p prime at x subtract f at x q prime at x divided by q at x. Then, not much you can do with it except for one little thing on the right side of that expression. If you take a look at f at x, it might occur to you that f at x, according to the original information, is equal to p at x divided by q at x. And then that's times q prime at x, and all this over top of q at x. Now we've been here before, and there's actually two ways that you can deal with this. It's a complex fraction on top. So the normal procedure would be to get a common denominator of q at x on the numerator and then divide out the complex fraction. The other thing that you can do, however, is you can multiply by, and I think I've shown this earlier, we can multiply by q at x on top and then times q at x in the bottom, because that's just multiplying by 1. And as long as everybody gets the treatment, then it's really just combining those steps, that getting the denominator and then dividing by dividing out the complex fraction. So if I multiply everything by q at x, I will get p prime at x multiplied by q at x. And then the second term multiplying by q at x will just eliminate that denominator, so we get p at x times q prime at x. And then the denominator becomes q at x times q at x, which is q at x squared. Now that is the product, or the quotient rule. So the derivative of the numerator, p at x, times q at x, subtract p at x, the numerator, times q prime at x, divided by the quotient, q at x, the denominator, squared. So it is proven. So we don't have to worry about that anymore. Now let's go back and do a few questions then, back to where we were. And I'll show you the method that I use. You will find later on that it is possible to bypass the quotient rule and just use the product rule. And there are people who prefer that. I don't think it's really a good idea, but it does work. So we'll need the chain rule in order to do that. This one, the quotient rule always seems a little more complicated, but in fact it does have some advantages even in the simplification end of things, as we'll see later on. So u is equal to 3x minus 5. I do what I had done before. So u prime is equal to 3. And meanwhile, v is equal to x squared plus 5. So v prime is equal to 2x. So y prime is equal to u prime v minus u v prime all over v squared. So the substitution can begin immediately. So y prime is equal to u prime 3 times v, which is x squared plus 5, minus u, which is 3x minus 5 times v prime. So I'll put the v prime first, put the monomial first. 2x times 3x minus 5. And then all this is divided by v squared. So x squared plus 5 to the exponent of 2. Sadly, we will have to clean up that numerator in order to get like terms together. So 3x squared plus 15 minus 6x squared plus 10x all over x squared plus 5 to the exponent of 2. So y prime is equal to 3x squared minus 6x squared is minus 3x squared, and then plus 10x minus or plus 15. And then all over x squared plus 5 to the exponent of 2. Now the only thing is with this problem at this stage is, do you go further with it? And there's always that temptation to factor the numerator, and you can. And normally you don't have to. If there is a cancellation, then you should do so. So most people will try to factor. I don't think this thing factors anyways, but there's no chance that it will divide out one of the factors on the denominator, x squared plus 5. So I'm not going to bother, and typically that's how it works, and that is the general rule. If it leads to a simplification, then you do it. If it does not, then you don't. Now, number 2, I'm not going to worry about this one. I'm going to bypass it because it is, it doesn't really break a lot of new ground. If you do want the answer for your own work, f prime at x is equal to 4x squared plus 14x minus 5 all over 4x squared plus 5 to the 2. So check it out if you want, but I'm going to move on to the next one, which will challenge us a little bit more. So y is equal to the root of x plus 4 divided by the root of x minus 4. Interesting with this one, too, that the denominator is all one radical, but the numerator is not. I don't know if I did that on purpose or not. But whatever, we take what we're given. So don't forget that this could be written as x to the 1/2 plus 4. And then the denominator. Actually, I need to correct myself. I will treat this as just the square root of x. Right now, we can't handle those bracketed expressions. So, okay, it should be root of x minus 4, like that. Now, by the way, some of you would have rationalized the denominator or the numerator in this case. Would have been fine. I'm not going to. I'm going to stick with basically what I have, but do make that correction. And then, our u is equal to x to the 1/2 plus 4. So u prime, take the derivative of x to the 1/2, we get 1/2 x to the negative 1/2. And then v is equal to x to the 1/2 minus 4. So v prime is equal to 1/2 x to the negative 1/2. And then we just go further with this. Y prime is equal to u prime v minus u v prime all over top of v squared. So y prime is equal to 1/2 x to the negative 1/2 times v, which is x to the 1/2 minus 4, and then minus v prime, which is 1/2 x to the negative 1/2, multiplied by u, which is x to the 1/2 plus 4. And then this will leave us with, on the denominator, v squared. So x to the 1/2 minus 4 all squared. And now we have a choice. And in this case, the choice isn't going to be a big problem. But there really are two things we could do with this one. We could either distribute the 1/2 x to the negative 1/2 in to both of these, gather up the like terms, which is a nice idea. It will work because there will be like terms in this case. We can tell really by looking at it. Or what you can do is factor out a 1/2 x to the negative 1/2. Now we're going to be seeing this a lot in the future when we start doing the chain rule, but it's a good opportunity right now. If you think back to the factoring section that we did, dealt with common factors. And if you have a common factor for both of these clusters, you might as well remove it. And if you do, it'll leave you with this. 1/2 x to the negative 1/2 comes out. Now this one's almost too easy because when we divide that first factor by that, we get x to the 1/2 minus 4. And when we take it out of the second one, put a little bracket around that one even though we don't need it, we will be left with x to the 1/2 plus 4. Close this, and then close this, all over top of x to the 1/2 minus 4 squared. Then we can simplify the inner bracket. So we get x to the 1/2 minus 4 minus x to the 1/2 and then minus 4. And then this is all over top of x to the 1/2 minus 4 squared. I'm going to have to take an arrow and go over there, but you see where this is taking us. We'll have that 1/2 x to the minus 1/2 there, and then in the brackets minus 4 is minus 8, and that's all over x to the 1/2 minus 4 squared. And then gives you y prime. Negative 8 times 1/2 is negative 4, and then x to the negative 1/2 over x to the 1/2 minus 4 squared. Now this is okay, but you may see that other people will take, and we'll be a little more careful in the future, but you could take that x to the negative 1/2 to the bottom and write that as x to the positive 1/2 multiplied by x to the 1/2 minus 4 squared. You cannot distribute that x to the 1/2 in, however. Now, unless the question says write it with positive exponents, not a big deal. So the first one is there. But you have to be aware, because just for checking your answers, you want to make sure that what you have is right. So this does force you to do a little bit of post-question comparison. Don't view it as a huge problem, though. Now let's move on to the next question. Do a few more, and then I will break this lesson into two. Here we have y is equal to the root of x over 1 minus 5x squared. Pause me and go through this one on your own. Probably a good idea. X to the 1/2 over 1 minus 5x squared. I don't think you're going to find this one is going to amaze you too much. U is equal to x to the 1/2. So u prime is equal to 1/2 x to the negative 1/2. Meanwhile, v is equal to 1 minus 5x squared, and v prime is equal to negative 10x. So y prime is equal to u prime v minus u v prime all over v squared. So y prime is equal to 1/2 x to the negative 1/2 times v, which is 1 minus 5x squared, minus u, which is x to the 1/2 times v prime, which is negative 10x. And this is all over v squared, so 1 minus 5x squared all squared. Now once again we have choices. Some of you would say, I'm going to factor out an x to the negative 1/2, and you'd be doing fine if you did that. The other choice would be, because we don't have a very complicated second cluster, you may just want to multiply that negative x to the 1/2 times negative 10x. That's going to work out pretty well too. And so that's not going to be a big deal. So you will have these choices, and you just really have to decide what you want to do. Both will lead you to the same place, although you may have to suffer with one if you're not careful with fractions. So what I'm going to do is I'm going to do it strictly by the book. I'm going to factor out the LCD, or greatest common factor, would be x to the negative 1/2. You always take out the lowest factor of x from both clusters. Now I know you could multiply that in, giving you x to the 3/2. So I mean, keep in mind that's a fine method to do it. I'm also going to take out a factor of 1/2. So I'll eliminate my fractions. And let's see where this takes us. So the 1/2 x to the negative 1/2 is removed, and when we divide that out of the first term, that cleans us out, and we're left with 1 minus 5x squared. Put a little bracket around it, even though we don't need that one. And then minus, when we take out, we divide by 1/2, we let it be multiplied by 2. So be careful with that. That'll give you 1 divided by 1/2 is 2. As well, when you divide by negative 1/2, you multiply or you subtract. So be really careful. I'm not showing this in as much detail as I did in the pre-calc unit, but 1/2 minus negative 1/2 is x to the 1. And then we still have a factor of negative 10x. So I'm doing this method almost as a preview of what we have to do later on, so we get comfortable with it. It would have been fine just to distribute it and get the like terms, but this is kind of a nice method. So what we get now, if we continue on with this path, is 1/2 x to the negative 1/2. Inside that bracket, we have 1 minus 5x squared plus 20x squared. And then this is all over 1 minus 5x squared all squared. And therefore, y prime is equal to 1/2 x to the negative 1/2 multiplied by, in a bracket, 1 and then plus 15 x squared all over top of 1 minus 5x squared to the 2. Now the only other thing that I'm going to do with this question to finish it off, dy dx, or maybe the only other thing, we have a factor of 1 minus 5x squared to the 2, and we have this factor on top of 1 plus 15x squared. But I'm going to take the x to the negative 1/2 to the bottom to make it positive, and the 1/2. So you want to be careful, because this 1/2 could be written with a denominator of 2 on the bottom. So it's better not to have the complex fraction and write it as a single regular numerator-denominator fraction. So 1/2, put the 2 on the bottom, keep the 1 on top. And the way I've got it now is just 1 plus 15x squared on top. Nothing else is left. So the 1/2 should be dealt with. And had you got the like terms together, I'm just going to circle this off, had you got the like terms together through distribution at the beginning, what you would have noticed was you would have had more fractions around. So the real reason I did factor out that 1/2 x to the negative 1/2 was so that I didn't have to deal with the fractions. I didn't want to have many terms with the fraction, because it's bad form to leave a fraction within a fraction. So by factoring out the 1/2, as we did in the pre-calc factoring unit, it allowed me to just have one fraction term, and then I could put it to the denominator like that. So it's a cleaner look. Now I'm going to stop right now, and then there is another question on the next. Actually, I'm going to do that last one. Excuse me, change my mind, and then I'll leave the other ones. So the reason I chose this one is this is an example where, although the quotient rule works, much easier to simplify first. So m at x is equal to, first off, x to the 1/3 over x to the 1/2. So that x to the 1/2 on the bottom, the denominator, belongs to each of the terms on top. And then we can turn this into just a regular question that does not require us to use any of the rules. So this is 1/3 minus 1/2. We subtract exponents, plus x to the 1 minus 1/2, plus 3x to the negative 1/2. And then m at x is equal to x. When you subtract these, 2 over 6 minus 3 over 6 is minus 1 over 6. Check that one out. Make sure that you get that one right. And then plus x to the 2 over 2 minus 1 over 2 is 1 over 2. And then 3x to the negative 1/2. So now, m prime at x is equal to negative 1 over 6. X subtract 6 over 6 will give us negative 7 over 6 plus 1/2 x to the negative 1/2. And then 3 times negative 1/2 is minus 3/2 x to the negative 3/2. Now, had you used the quotient rule, what would have happened is that you would have had a different expression at the end because you would have had just one denominator. So it will look different, but it still would be correct. So note, if you had used the quotient rule, answer will look different. Nothing you can do about it. You can go from one point to the other. Like if you did get an LCD for 6, 2, and x, also with your negative exponents, it will work. I chose this because it's a simpler route. There's nothing wrong with using the quotient rule, except, it does throw in a few extra steps. Now I'm going to stop right there. There will be a second part to this lesson where we'll go through some simple sort of applications, nothing that's going to really shock you, I think. Thank you for your time.